Hello everyone. Hope you are doing very well. Today, as you all know, that we are going to cover the part 8 of theory of the chapter coordination compounds, right? So let's begin our today's topic, that is NCERT chapter 5 coordination compounds, theory part 8, and today we are going to cover the NCERT section 5.5.5 to 5.7. This is disclaimer. Objective of today's lecture. So after attending this lecture, you will be able to appreciate the importance and the applications of coordination compounds in our day-to-day life. So today we are going to discuss the importance and applications of coordination compounds. The topics that we are going to cover today according to the NCERT is the section 5.5.5, the some part of this topic, that is color of coordination compounds, and the section 5.6, which is bonding in the metal carbonyls, and then the section 5.7, that is importance and the applications of coordination compounds. So let's begin with our first topic, the color of coordination compounds. So let's see the color of some compounds which is formed by the coordination complex, like some gemstones. Okay, so let's see the color of some gemstones. First of all, let's cover ruby. Ruby is a gemstone. You have probably heard about it. Chromium 3 positive. Ruby is mainly aluminium oxide. Okay, Al2O3. Ruby is aluminium oxide, Al2O3. Chromium 3 positive integration in the ruby. Now, how the chromium 3 positive is going to introduce in the ruby? Chromium 3 positive ions are scattered randomly throughout the alumina lattice. Okay, ruby is mainly aluminium oxide. The lattice of the aluminium, you can call it alumina lattice, or we are calling it here as alumina lattice. And throughout this lattice, throughout this structure, the ions of the chromium 3 positive are scattered randomly, taking the places usually occupied by aluminium 3 positive ions. Chromium 3 positive in the ruby. Now, chromium plus 3 species are incorporated as octahedral chromium plus 3 complexes built into the alumina lattice. So try to understand that chromium in the plus 3, this species are incorporated as octahedral chromium plus 3 complexes built into alumina lattice. So inside the alumina lattice, inside the structure of this aluminium oxide of the ruby, the chromium plus 3 complex in the octahedral form are incorporated as a chromium plus 3 species. This is how the rubies is going to, or you can say chromium 3 positive is going to be there in the ruby. Ruby's color. So DD transitions specifically in this specific environment result in the ruby's red color. So why the color? Because we have studied about the DD transition. That DD transition happens between the ground state to higher excited state by absorbance of some wavelength of light, due to which it exhibits the complementary color of the absorbed light. And due to this transition, DD transition and the of electrons, so in this specific environment, this DD transition result into the red color of the ruby. So ruby gem is going to exhibit red in color. You can see this image, which is figure 5.12 according to the NCERT textbook. This is a ruby gemstone. It was found in the marble from Mogok, Myanmar. So this is the image collected for this sample of ruby, which was collected from Mogok, Myanmar. You can see clearly it is red in color due to the DD transitions in the specific environment of alumina lattice. Let's see our next gemstone, that is emerald. So for the emerald is the mineral beryl. Okay, so what is emerald made up of? Emerald is basically a mineral beryl. Formula is BeR beryllium whole thrice, aluminium whole twice, Si, silicon whole 6, and oxygen 18. These are the specific proportions of different atoms in this compound, in this mineral called beryl. Beryllium, aluminium, silicon, and oxygen. Chromium 3 positive integration in the emerald. Now, how the chromium 3 positive is introduced? So, this chromium 3 positive ions occupy the octahedral sites within the beryl mineral structure, as you have seen in the ruby, where the aluminum lattice, and inside the aluminum lattice, chromium 3 positive is occupying the spaces which is occupied by aluminium. Here, the chromium 3 positive ions occupying octahedral sites, octahedral spaces within the beryl mineral structure. So within this mineral structure, the octahedral site is occupying by the chromium 3 positive ions. Emerald's color mechanism, which is a key difference. So absorption bands for emerald are shifted to longer wavelengths. That means they absorb yellow, red, and blue light compared to the ruby. So absorption bands here, absorption bands means the specific region from which the light is going to be absorbed by the specific stone. So absorption band for this stone emerald are shifted to the longer wavelengths. That means it is going to absorb the wavelength of the light which is having longer wavelength comparative to the ruby. So the absorption bands for the emerald is shifted to the higher wavelength from which it is going to absorb the light of high wavelength compared to the ruby. That means they are going to absorb the yellow, red, and the blue light, higher wavelength lights. Okay. Emerald's color. Because shift in the absorption cause emerald to transmit light in the green region, giving it its characteristic green color. Okay. So the absorption, because absorption area is causing or shifting. Okay. Due to this absorption band shifting, it will cause the emerald to transmit light in the green region. Okay. So it is going to transmit the color as a green color. Okay. So you can see this is the image, which is the figure 5.12 of a emerald. This gemstone was found in Muzo, Colombia. So in the Colombia, this gemstone was found, and you can clearly see it is green in color. It is giving us its characteristic green color after absorbing the light from the shifted absorption bands to the longer wavelengths, right? Okay. Let's talk about our next section, 5.6, that is bonding in the metal carbonyl. So we have seen some applications of, in the nature of the color and the coordination compounds. Now we talk about the metal carbonyls and how the bonding is happening in the metal carbonyls. Let's first talk about homoleptic carbonyls. Homo is there. Homo means same. So something is going to be similar. So the definition of this particular topic is that homoleptic carbonyls are the coordination compounds where the only ligands attached to the central metal atom are carbonyl group. Okay, that's why we use the homo word here. That in a complex, in a coordination compound, there will be the central metal atom, right? And the ligand that are attaching with this central metal atom is only and only carbonyl groups, that is CO groups as ligands. So that's why we are calling them as homoleptic carbonyls. That means they are coordination compounds where only ligand present is carbonyl groups attaching to the central metal atom. How does this form the formation? So most transition metals are capable of forming homoleptic complexes. So there are many transition metals, or that's why we are using most word, that most transition metals are capable of this formation of homoleptic compounds. Key point here to remember that in the homoleptic carbonyls, the oxidation state of metal is always 0 or the lowest possible oxidation state. Okay. Why is it so? Because the charge on the carbonyl is 0, which will cause the charge or the oxidation state of the metal which is to which it is attaching to, it is bonding to be 0. Okay, so this is the key point, that when you take the example of a homoleptic carbonyl where the central metal is only attached with the same ligand, that is carbonyl group, the oxidation state of metal here always is 0, because the charge on the carbonyl itself is 0, which is why the oxidation state of metal will be lowest possible, or 0. Structures of mononuclear carbonyls. Mononuclear carbonyl means single metal atom will be there. So let's take the example. First example will be the tetracarbonyl nickel 0 NiCO whole 4. So its name will be tetracarbonyl nickel 0, and its formula, molecular formula, will be nickel CO whole 4. CO is carbonyl ligand. Okay, so this is a mononuclear carbonyl, a single metal atom carbonyl, where metal atom, that is nickel, is only one. Okay, so metal atom is only one. The structure will be tetrahedral for this, as you know. You can see that carbonyl is 4 in number. There are 4 groups of carbonyl that are bonding with the central metal nickel here, having 0 oxidation state on the nickel. So the structure of it will be tetrahedral. The oxidation state of nickel will be 0. We just have seen the key point where we are saying that in these type of homoleptic carbonyls, because of the presence of 0 charge on the carbonyl ligand itself, the oxidation state of metal is always 0. So here also the oxidation state of nickel will be 0. So this is the structure. You can see tetrahedral structure for this complex, nickel attaching with 4 ligand group of carbonyl. So this is NiCO whole 4, which is a tetrahedral structure formed in the tetrahedral manner. Okay, so this is the tetrahedral geometry or tetrahedral structure of this complex. The central metal atom is nickel, the ligands are carbonyl, and the oxidation state of nickel is 0, because there is no charge on the carbonyl ligand also itself. Now, under the same mononuclear carbonyl category, let's see the example second, pentacarbonyl iron 0. Okay, pentacarbonyl means 5 carbonyl ligands will going to be there in the complex. Iron will be the main or the single or the central metal, and having 0 oxidation state. So its structure will be trigonal biopyramidal. 5 ligands are there. Structure will be trigonal biopyramidal, and the oxidation state of iron will be 0 as per the concept. And this is the structure of trigonal biopyramidal geometry for this complex, iron bonding with 5 number of carbonyl groups in the trigonal biopyramidal geometry. Okay, this is how you can see the diagram or the structure for the mononuclear carbonyl, which is here pentacarbonyl iron 0, FeCO whole 5. Central metal is iron, 0 oxidation state on it. Ligands are carbonyl only. This is an example of homoleptic carbonyl. So let's see the again next example third, hexacarbonyl chromium 0. Hexacarbonyl means 6 carbonyl ligands will be there attaching with the central metal, which is chromium in this complex, having 0 oxidation state. The structure for this is octahedral. How? There are 6 ligands, 6 number of ligands that are surrounding the central metal, that are bonding with the central metal, right? So the structure will be octahedral. Oxidation state of chromium, the oxidation state of chromium will be here 0, because as per the concept, the chromium will going to be have 0 oxidation state. And this is the structure you can see for the octahedral geometry of this hexacarbonyl chromium 0 complex, where chromium is the central metal and 6 number of carbonyls are attaching with it through the bonds. So this is the octahedral geometry for this complex, chromium CO whole 6, where chromium is having 0 oxidation state in the, and this arrangement is octahedral. Okay. Let's see the structures of polynuclear carbonyls. Polynuclear means, poly means so many. So polynuclear carbonyls means we have multiple metal atoms. Okay, in a structure we have more than one central metal is going to be there. So what is going to be the structure of these type of carbonyls? So let's see the example first taken here. Deca-carbonyl diamanganese 0. Okay, deca means 10, carbonyl, that means carbonyl are 10 in number, diamanganese, that means 2 manganese are going to be there having 0 oxidation state. The formula will be M into CO whole 10. The composition, if you talk about, it will be composed of 2 square pyramidal MnCO whole 5 units. Okay, so 2 square pyramidal MnCO whole 5, that means there will be 2 units having square pyramidal structure. Each unit is having Mn as a central metal attaching with 5 number of carbonyls. So this is the group in the one unit. It is attaching with the another manganese unit and forming this complex decacarbonyl diamanganese. Okay, that's why we are writing here that it is composed of 2 square pyramidal MnCO whole 5 units. How is the bonding? So 2 units are joined by a direct manganese-manganese bond. Okay, so these 2 square pyramidal units are joining by through the manganese. So manganese is bonding with the manganese, Mn bond is there. So you can see the diagram for this particular complex polynuclear carbonyl, where 2 manganese are joining together, which is the central metal for for their own units, right? So manganese is the central metal here in this unit, which is a square pyramidal geometry, arranged in the square pyramidal geometry, and here 5 carbonyl are bonding with the central metal manganese. Similarly, this is the another unit, the lower one, where central metal is manganese and it is attaching with the 5 number of carbonyl groups, right? And when these 2 manganese are bonding together directly, then they form this complex by joining these 2 square pyramidal units of MnCO whole 5, giving us the structure of Mn2CO whole 10 or decacarbonyl diamanganese 0. Here also both the manganese is going to have 0 oxidation state because none of the ligand is anionic or having any charge. So carbonyl is also like neutral, it is not going to have any charge. So manganese will also going to be exhibiting oxidation number 0. Okay, so this is the structure of this complex decacarbonyl diamanganese 0, which comes under the polynuclear carbonyls. Let's see the another example of this polynuclear carbonyls. Example second, octa-carbonyl diacobalt 0. That means there are 8 number of carbonyl that are attaching with diacobalt, means 2 cobalt central metals, and the cobalt are having 0 oxidation state. The bonding here is that features a cobalt-cobalt bonding. So as we have seen in the manganese case also, in the previous example, here the bonding is between the cobalt and the cobalt, which is the central metal of both the units. So there is direct bonding between these 2 metals. Bridging ligands. So cobalt-cobalt bond is further strengthened by the 2 bridging carbonyl groups. Okay, you will understand this after seeing the diagram, that the 2 cobalt-cobalt bond which is forming. Okay, so there is a presence of cobalt-cobalt bond, but that is not direct. Cobalt-cobalt is further strengthened by the 2 bridging carbonyls groups. So that means between the cobalt and the cobalt bond, we have one attached carbonyl group which is going to give the strength to this cobalt-cobalt bonding. Okay, let's see how. This is the structure for the octa-carbonyl diacobalt 0, CO2CO whole 8, where this cobalt-cobalt bond is included. Okay, and there is this bridging forming between the cobalt-cobalt bond of the carbonyl, C double bond O group, right? So we are calling them as bridging carbonyl or bridging CO molecule. Right? So this is going to strengthen this structure, and the other 4 or other 3, because one is this, the other 3 carbonyl groups are attached with this cobalt in this manner. Right? So this is the structure of the CO2CO8, that is octacarbonyl diacobalt 0. And this is the main thing here to observe is that there is a presence of bridging carbonyl. So there is 2 bridging carbonyl groups which is forming in the cobalt-cobalt bond, which is kind of giving the strength to this structure, to this cobalt-cobalt bond. Okay. Nature of metal carbon bond in the metal carbonyls. That is synergic bonding. We are going to call it as synergic bonding, the bond between the metal and the carbon in the metal carbonyl. So in the metal carbonyls, there is a metal in the center, right? And that metal is attaching with number of carbonyl groups. Okay. How the bonding is happening? So basically that carbonyl is going to have C double bond O. Now from this C double bond O, C is going to make the bond with the metal. So what is the nature of that C bond, metal carbon bond in the metal carbonyls? This is the diagram, which is figure 5.14 in our NCERT textbook, which is showing the example of synergic bonding interactions in a carbonyl complex. You can see this is a metal, this is a carbonyl ligand, and this is how the bonding is forming. So metal is having their vacant d orbitals arranging in a particular geometry in a particular manner. Carbonyl is also having their particular orbitals, right? So what is happening? The sharing of the electrons is happening, right? So this sigma bond is forming by the donation of lone pair of electrons on the carbonyl carbon to the vacant orbital of the metal. Okay, you can see that carbonyl carbon lone pair of electron of this carbon is going to be shared to this vacant orbital of metal, which is why this direct sharing is happening, which is forming sigma bond between the metal and the carbonyl. Here you can see pi bond is also forming. This pi is also written here, right? How? So the donation of electron from the filled d orbital. This is the orbital which is filled having some electrons. Now this electron in this filled d orbitals of metal is going to be donated to the vacant anti-bonding, that is pi star orbital of the carbon monoxide or carbonyl. Okay, so this filled d orbital electron is going to be donated to the anti-bonding orbital of carbonyl, due to which pi bond is forming between the metal and the carbonyl. Okay, so this is what we are calling as synergic bonding in the metallic carbonyls. That means both sigma and pi bonds are forming between the metal and the ligand. Basically, this synergic bonding is strengthens the bond between the carbonyl and the metal usually. Metal carbon bond is unique because it possesses both sigma and pi character, leading to a synergistic effect. As I said, that metal carbon bond which formed here is unique. Why? Because it is possessing both sigma and pi character, leading to its synergic effect. Metal carbon sigma bond. If you talk about the metal carbon sigma bond, which is ligand to the metal donation. Okay, ligand donates lone pair to the vacant d orbital of metal. So it is formed by the donation of lone pair of electrons from carbonyl carbon to the metal. It goes into the vacant empty orbital of the metal. So from the lone pair of electrons present in the carbonyl carbon, it is going to donate into the vacant or empty orbital of the metal, and this is how the sigma bond formed, or you can say metal carbon sigma bond formed, which is ligand to the metal donation. Now, if you talk about the another bond, that is pi bond. So metal carbon pi bond, which is from metal to the ligand back donation. This is back donation in the pi star orbital of the carbonyl, right? So metal carbon pi bond happens, or pi bond forms when metal gives electron to the ligand by back donation. So it is formed by the donation of pair of electrons from a filled d orbital of metal. Okay, so filled d orbital of d orbital of metal is going to donate its pair of electrons to the ligand. So it will goes into the vacant anti-bonding or pi star orbital of the carbon monoxide ligand. Okay, so this filled d orbital of the metal is going to donate its electron to the vacant anti-bonding or pi star orbital of carbon monoxide, which is ligand. So this is often called pi back bonding or back donation, because metal is giving its electron to the carbonyl anti-bonding orbital. So this is a back donation or pi back bond because of pi character. Now the synergic effect. So if you explain sigma donation from carbonyl to the metal increases the electron density on the metal, right? This is so simple that if the carbonyl ligand is going to donate its electron to the metal, then the electron density in the metal or on the metal is going to increase. Increased electron density or increase in the number of electrons is then effectively delocalized back to the carbonyl ligand via the pi back bonding. And due to this increasing or increase in the electron density, increase in the electron number, this effectively delocalize back to the carbonyl. So this will unstable. This will make the metal unstable after the increasing of the electron density, right? So it only wants a certain number of electrons on it. So due to this increasing electron density, this is going to delocalize the electrons back to the carbonyl now via pi back bonding. Not directly, but via pi back bonding by donating the electron to the pi star anti-bonding orbital. So this is a reciprocal process. That means ligand will give the electrons to the metal by sigma donation, and the metal gives the electron to the ligand by pi back donation. Now this will create a synergic effect. This is what we are calling as synergic effect. Okay, so this is a name. This is not like you are like you are going to understand through its meaning or something, but it is a term which we are given or which we are giving to this nature, to this reciprocal process which is happening in this metal carbonyl bonding. So the result of this is that synergic bonding significantly strengthens the bond between the carbonyl ligand and the metal center. So the synergic bonding or synergic effect happening between the carbonyl ligand and the metal is going to strengthens the bond between the carbonyl ligand and the metal center. Okay, so the structure or the complex is going to be more you can say strong, okay, or stable. So this is why the synergic bonding we are talking about. That synergic effect strengthens the bond between the carbonyl and the metal, because the both type of character is possessing, like pi character also is coming and sigma character is also coming. That's why the bond is strengthening or become strong. Okay, let's move to our next section, that is 5.7. Importance and application of coordination compounds. So let's see the uses of coordination compounds in the various fields. Widespread presence and functions. Okay, so there are so many presence and functions of the coordination compound in the various fields. Let's see how. So it is found in mineral, plant and the animal world also. Okay, so mineral you can say coordination compounds are found in mineral, plant and the animal world. They play vital roles, very important roles or very different roles in the analytical chemistry, in the metallurgy, in biological systems, in the industry and medicine industry also. Applications in the analytical chemistry. So if you only talk about the analytical chemistry, qualitative and quantitative analysis. In the qualitative or the quantitative analysis, we use this coordination compounds for both detection and the estimation of the substances. Detection means we have to identify. Okay, that means we have to detect whether it is present or not. Then we use coordination compounds for some metals, for some ions. Okay, in the analytical chemistry, and for estimation of the substances also we use coordination compounds. Basis for analysis. So coordination compounds. So the color reactions formed by the metal ions with the ligands, especially the chelating ligands, they are the foundation for this analysis in the analytical chemistry. Okay, because color is denoting so many things. Like if the coordination compound is exhibiting color differently with different ligands, right? So these color reactions which are formed by metal ions with the ligands, especially when they are forming the bond with the chelating ligands, then they exhibit these different colors. They are the foundation for the analysis of the analytical chemistry. The methods. So basis for detection and estimation by the classical and the instrumental methods. We use either classical or the instrumental methods to use these coordination compounds in the analytical chemistry. Examples of the reagents like EDTA. EDTA is a coordination compound which we use as a reagent in the analytical chemistry. DMG, which is dimethyl glyoxime. Alpha nitroso beta naphthol, this is the another reagent, and cupron. So these are the reagent comes under the coordination compound which we use as a reagent in the analytical chemistry. Estimation of water hardness. So there is the water hardness thing which estimated by the method of simple titration with Na2-EDTA. Okay. Now we are here doing the titration with this coordination compound Na2-EDTA. The mechanism involves the calcium 2 positive and the magnesium 2 positive ions, which are the causes of hardness due to which the water gets hardened. So calcium 2 positive and magnesium 2 positive ions which cause hardness, they form stable complexes with the EDTA, which is why we do the water titration or the titration with Na2-EDTA due to which what will happen? These ions, which are the main cause of hardness, they are going to make the stable complex with the EDTA and the water hardness will remove. Selectivity. So selective estimation of calcium 2 positive and magnesium 2 positive is possible due to the difference in the stability constants of calcium and the magnesium complex. Because the stability complex because the stability constants are different for the calcium and the magnesium complexes, we can selectively estimate the calcium 2 positive and the magnesium 2 positive ions. Okay, due to this difference in the stability of their due to this difference in the stability constant of their complexes. Okay, so this is how we can use the coordination compounds in the estimation of water hardness. Next is metallurgy, which is a process of metal extraction. The role, so utilized in the important extraction processes for metals. So what is the role of the coordination compounds here? That they utilize in most important extractions processes for different metals. For example, gold extraction. If we are extracting the gold, then we are going to use these. And gold combines with the cyanide ion, Cn negative, in the presence of oxygen and water to form the soluble coordination entity, which is AU, that is gold, Cn whole twice, whole negative. This is a complex, a coordination entity which is soluble, which is formed when the gold combines with cyanide in presence of oxygen and water in a like normal conditions. Okay, so because oxygen is available, water you can add simply, and then gold can combine with cyanide, form this soluble coordination entity, and through this we can extract the gold. Metallic gold is then separated from the solution by adding zinc. Now, in this complex, we are getting this complex, and we know this complex is made up of gold, right? So we are extracting the gold. But now, if you want to take the metallic gold from this, so the metallic gold is separated by adding zinc into it. So there is Mark Arthur Forrest cyanide process, which are known for gold and silver that are leached with cyanide ion. So 4 gold plus 8 Cn negative plus 2 water molecules plus oxygen. The presence of oxygen and water, when you add the cyanide with the gold, it is going to form this complex of gold, Cn whole twice whole negative plus 4 hydroxyl ions will be removed. Now, when you add the zinc into this complex, so when you add this complex into and zinc into it, the metallic gold you are going to get plus zinc cyanide whole 4 whole 2 negative is the complex that you are going to get as a extra product or side product. Okay, so the you can say zinc will going to replace the place of gold here, or you can say that cyanide as a ligand is going to replace the place from this complex to make the complex with the zinc and bonded with the zinc. Okay, so this is how the extraction of the gold is happening, and we use the cyanide ligand and the formation of the coordination compounds in these extraction processes for the metal extraction in the metallurgy. Next is purification of metals. So the principle included is that metals can be purified by first forming a volatile or a soluble coordination compounds, and then subsequently decomposing it to yield the pure metal. This is the principle we are going to follow for the purification of metals. Let's take the example of nickel purification, which is also has a name called Mond's process. Okay, here we do the impure nickel is going to reacted with carbon monoxide to form the tetracarbonyl 0, which is again metal carbonyl we just have studied, right? Nickel CO whole 4. So impure nickel, we want to purify the nickel, right? So we take the impure nickel and then we react it with the carbon monoxide to form this tetracarbonyl nickel 0 metal carbonyl complex, which is a volatile coordination compound. Okay. Now this nickel carbonyl or this tetracarbonyl nickel is then heated, causing it to decompose and yield the pure nickel. So volatile means it is easily can be converted to the vapor. Okay. So when this complex is heated, it is decomposed and yield the pure nickel, thereby effectively separates the nickel from its impurities. So from the impure nickel, we get the pure nickel by this process, by firstly formation of this complex by reacting with the carbon monoxide and then heating it to get the pure nickel after removing its impurities. Reaction involving our nickel, first of all, is reacting with the carbon monoxide in 50 to 60 degrees Celsius temperature range. It is forming this complex nickel CO whole 4 where we are having the impure nickel. Now for getting the pure nickel, we heat this NiCO whole 4 in the range of 180 to 250 degrees Celsius temperature, and you get a pure nickel from it plus 4 carbonyl as a side product. So this is the process of nickel purification or Mond's process, where we are using the concept or using the coordination compounds. Let's see next uses, which is in the biological systems. Coordination compounds are crucial for life and perform numerous vital functions within the living organism. How? First is chlorophyll. So the function of it is pigment responsible for photosynthesis in the plant. The plant is having green color, or the pigment which is present in the plant. That is why it is so in the plants. This is responsible for the photosynthesis in the plants. So chlorophyll pigment is responsible for the photosynthesis happening in the plants. And the metal ion here is the coordination compound of magnesium, that is magnesium 2 positive. Magnesium in the 2 positive is going to be the metal ion. Next example with the living organism is hemoglobin. So the function is red pigment in the blood that acts as an oxygen carrier. So this is a red pigment present in our blood, in the human blood, that will act as an oxygen carrier throughout our body in the various, veins and arteries and the heart. So metal ion, so coordination compound of iron. The metal that is going to be present in the coordination compound inside the hemoglobin is iron in the 2 positive oxidation state. Next example is vitamin B12, which is cyanocobalamin or cyanocobalamin. So the function of it is anti-pernicious anemia factor. And the metal ion involving in the vitamin B12 is coordination compound of cobalt 3 positive. So cobalt in the 3 positive is the metal ion, which is going to be there in the coordination compound present in the vitamin B12. Let's see the next field in which we use the coordination compound, industrial catalysis. So coordination compounds are widely employed as catalyst in the various industrial processes. In the various industry process to either form something or like find something, we use the coordination compounds as catalyst. For example, let's take Wilkinson's catalyst. Okay. Now, catalyst is rhodium complex, that is PH3P whole thrice RHCl. This is a rhodium complex having name Wilkinson catalyst. The application of this complex or this catalyst is that it is used for hydrogenation of alkenes, that is adding hydrogen across a double bond. That means double bond is converting to the single bonds, or you can say hydrogenation of alkenes. For this process, we use rhodium complex or Wilkinson's catalyst to increase the rate or the speed of our reaction. Next use is in the field of electroplating. Improved plating quality. What it do? So articles are electroplated with the silver and the gold more smoothly and evenly from the solutions of their complexes. For example, the example of complexes are silver cyanide whole twice whole negative and gold cyanide whole twice whole negative. These are the complexes that are used instead of the simple metal ion solutions for the electroplating of the articles of inside this. So in the electroplating field also we use this plating of the complexes of silver and the gold instead of the simple metal ion solutions for the plating matter, which will going to improve the quality. Next is black and white photography. You know about the black and white photography, right? So fixing process. Now developed film is fixed by washing with hypo solutions. That means sodium thiosulfate solutions. Okay. So in the black and white photography, we have this fixing process where the developed film is fixed by washing with the hypo solutions. That means sodium thiosulfate solutions. The mechanism include that hypo solution is dissolved undecomposed silver bromide by forming a soluble complex ion, which is silver S2O3 whole twice whole 3 negative. This is the mechanism involving in this kind of photography, that hypo solutions or sodium thiosulfate solutions. Okay, this dissolves undecomposed silver bromide by forming the soluble complex ion of the silver. So AgBr plus 2S2O3 2 negative, and this is going to form this complex AgS2O3 whole twice whole 3 negative plus give us the bromide ions. Okay, so this is the mechanism involving in the fixing process in black and white photography, where we are using the coordination entity. This. Next field where the coordination compound are used is medicinal chemistry, where chelate therapy is famous. So the purpose of this is treatment of toxicity caused by the excess metals in the biological systems. Okay, if excess metals are there in biological system, then the toxicity which it creates, the treatment of that toxicity is the purpose of this, therapy. The mechanism is that chelating ligands form stable coordination compounds with the toxic metals, facilitating their removal. So, chelating ligand means the ligands which formed several bonds with the central metal form a ring-like structure around the central metal, and these ligands form stable coordination compound present with the toxic metals present in the biological system, which facilitate their removal easily. The example of treatments are excess copper. So if there is excess of copper metal, then it is removed by D-penicillamine. If there is excess of iron, it is removed by desferrioxime B. If there is lead poisoning, then it is treated with EDTA. Anti-tumor agents, they also like we use this in the as an anti-tumor agent also. So certain platinum coordination compounds inhibit the tumor growth. Okay, there are some platinum coordination compounds where the central metal is platinum, which cuts the tumor growth. For example, cisplatin and related compounds. These are the example of those platinum coordination compounds which inhibit the tumor growth. So they are acting as an anti-tumor agents. Okay, let's cover the summary that we have covered today. So first we have covered the color in the ruby and emerald, where we see that both the ruby and emerald get their color from chromium 3 positive in the D3 configuration ions, which is located in the octahedral sites within their respective crystal lattices. Colors are produced by the DD electronic transitions between ground and the higher energy level of these chromium 3 positive ions. We then talk about the homoleptic carbonyls, where the metal is going to have zero oxidation states and the metal is going to have only bonded with the carbonyl ligands. Structure is like nickel CO whole 4, which is tetrahedral, FeCO whole 5, which was trigonal biopyramidal, and chromium CO whole 6, which is octahedral in structure. Then we see the polynuclear carbonyl, which is having MM bond, that is metal-metal bonds, and also some are including with bridging carbonyl, which is going to strengthen the structure of the complex. We also see in the synergic bonding concept, where the metal-carbon bond found by the carbonyl electrons with the metal electron sigma donation and metal electron to the carbonyl ligand pi back donation. Okay, and this synergic effect is going to strengthen the bond between the carbonyl and the metal. Then we have talked about the applications in the analytical chemistry of coordination compounds. So we use the coordination compounds in the analytical chemistry for the detection and the estimation, especially the water hardness, where we use the EDTA. And we use it in metallurgy for the metal extraction like gold with the cyanide, and purification for the metal, like for example in the Mons process for the nickel metal. Then we have seen the next field in which coordination compound is used, which is biological systems, where the essential roles are played in the chlorophyll by magnesium, in the hemoglobin by iron, in the vitamin B12 by cobalt, and many enzymes. We also use the coordination compound in as an industrial catalysis. So it is act as a catalyst, for example, Wilkinson's catalyst. Medicinal chemistry is also a field where chelate therapy was there, in which it includes the removal of toxic metals. For example, we use EDTA for the lead, and it will act as anti-tumor agents also, like cisplatin we have seen. Okay, thank you so much. That's all for today's chemistry session. Thank you.